If we are in 7.2, we haven't finished this one. Okay, so we continue with the 7.2. Basically, what we are going to do is, we would like to know how we're going to solve differential equation. Let's give it this title because we already checked the other parts. So solving, if you like, solving linear differential equations using Laplace transform. Yes.
Is this supposed to be 7.3?
No.
Is it this configuration?
Yes. Yeah, we didn't finish it that. This is the big one that we didn't. That's why I just give it the title, this one, so that you pay attention. Okay. So solving linear differential equation using Laplace transform. We did the preliminaries, okay, Laplace transform, but we didn't apply it. That's it. That's the case. Now, in order to do it, we need this theorem. We need to find a connection between Laplace transform of one function and the Laplace transform of its derivatives. Because the equation that we're going to solve would have something like what? Y double prime, Y prime, Y. So this theorem will do it for us. Okay, theorem. Okay, so this theorem will give you the Laplace transform of derivatives again. Okay, this is it. So the function is going to be this one. If we have a function, let's say if I start with the preliminaries, then I expand it. If the function f, okay, the function f is differentiable, okay, it's going to be differentiable. You know, it's going to be differentiable on, let's say, positive numbers or whatever on, okay, let's have on 0 and positive infinity. Then if you have a Laplace of f prime of t, this is going to be equal to the s times Laplace of f of t minus f of 0. So if we know the Laplace of f of t, then we can find the Laplace of the f prime of t. Okay, so the Laplace of f prime of t is equal to the s times Laplace of f of t minus f of 0. That's for the first derivative. If we can do this one, then we can come back, replace the f by f prime, we find Laplace of f double prime. Okay, let's prove it. It's not bad to see how you prove this one. Okay, prove. Write the definition. So the definition of a Laplace transform. So Laplace of f prime of t is going to be equal to what? Is equal to the 0 to infinity. Okay, e to the negative st f prime of t dt. Okay, so that's going to be the case. Now I want to relate it to the Laplace of f of t. So let's work on this integral that we're going to have. You say in order to find this integral, I want to change it to the f of t. In order to change it to the f of t, I'm going to use the integration by parts. Okay, so that's it. So note that what we are going to do is we are going to have e to the negative st f prime of t dt. So what I'm going to do, I'm going to consider u to be e to the negative st and the dv to be equal to the f prime of t dt for the integration by parts. Okay, so what's going to be du? Now du would be du derivative with respect to the t would be negative s e to the negative st. Okay, and if you integrate this one, if you like, that give you f of t. So if you go back and rewrite it, this is e to the negative st f prime of t dt. You can go from 0 to something like b first, and then take the limit when b goes to infinity. So that give you u times v. Okay, uv would be e to the negative st f of t. Okay, to going from 0 to b. Then minus integral of, okay, v du. So it's going to be v, and this is your du. So that's going to be what? F of t times it by negative s e to the st dt, and going from 0 to b. Okay, so this is going to be the case. Now let's simplify it a little bit. If you substitute, so that give you e to the sb f of b minus, if you replace the t by 0, so what do you get? It's going to be e to the 0 f of 0. Okay, minus this integral. And integral is respect to the t, so s is a constant. So I'm going to bring the negative s out, so that makes it to the negative positive. So this would be a plus s integral of 0 to b e to the negative st f of t d of t. Okay, just moving around to just change it to the format that we are interested in. So e to the 0 is 1. So this is going to be equal to, it's going to be f of b on the top, e to the sb down the bottom, minus f of 0. And this is going to be s integral from 0 to b, e to the negative st ft dt. Now, if you take the limit when b goes to infinity, this would be 0. Because b is, b is a positive number. And this integral, okay, so if you like, if you let t goes to infinity, okay, let t goes to positive infinity. If t goes to positive infinity, this integral would be 0 to infinity. It's the one that we are interested in. E to the negative st f prime of t dt. Okay, this the first part would be 0. Because f of b is a number, 1 over e sp. So that making it to the 0 minus f of 0. And this would be plus s integral from 0 to infinity. Okay, 0 to infinity, e to the negative st ft dt. That's it. This is Laplace of f prime of t is equal to, okay, so it is going to be equal to, okay, this is it. Can you see? That's going to be f prime of c. So this part is going to be s times Laplace of f of t minus f of c. See, this is the way you prove that we can express, okay, we can express the Laplace of, okay, we can express the Laplace of, just want to make sure you can see it. Okay, so we can express the Laplace of the f prime of t in terms of the Laplace of f of t. Any question? Now, if your function is going to be differentiable, we can replace the f by f prime. Okay, so note that you can extend this formula. Okay, so the extension is going to be the extension is this one. Note that if, okay, one can, if you like, one can replace f by f prime. So what's going to be the result? If you replace f by f prime, then you are going to have, so this will be the Laplace of f double prime of t is equal to the s Laplace of f prime of t minus f prime of 0. Okay, I'll just switch it. Now the Laplace of f prime of t from this formula, if you substitute, so what's going to be the result? It's going to be equal to the s, okay, s times what? X times, let's say, s Laplace of f of t minus f of 0, okay, f of 0, then minus f prime of 0. If you expand it, you have a formula for f double prime. Laplace of f double prime of t is going to be equal to the s squared Laplace of f of t minus s f of 0 minus f prime of 0. So this is going to be where we get the second derivative. And we can extend it to any notion that we like. You see the way we do it? This is the second order. So it's going to be s squared. S squared times the Laplace of t. Then you lower the power of the s. This is s to the second power. There's going to be s to the first power, f of 0. Then s to the 0 power, f prime of 0. So we start with the 1. The first order, SL of t first, minus the power of s done, s0. Then you can change it and you can write it in any form. You can try the third order, see if you can write it down. You want to try? Similarly, how about the Laplace of the third one? The third order is going to be equal to, it's going to be s cubed Laplace of f of t minus, you lower the power of the s squared. S squared times f of 0. You lower it again, minus s, but f prime of 0. You lower it again. It's going to be s to the power 0, but you get f double prime of 0. So if you start with the FTRs, the third order, you end up with the second here. 1 dot. Okay? So that would be the order that you're going to have. You want to get the general one? So what's going to be the general one? If you have a Laplace of the n order of t, okay, derivative, okay, the n order derivative of f of t is equal to the first one is going to be s to the n Laplace of f of t. That's the first one. You lower the power of the s to the n minus 1, s to the n minus 1, f of 0, minus s to the n minus 2, f prime of 0. You continue. You continue minus, what's going to be the last one? You see, this is to the n. This is to the n, 1 done. It's going to be f to the n minus 1 at 0. So that's going to be the general formula for the Laplace transform of any order of the derivative of the function, which is going to be very useful. We can go solve it, or we can apply it to any differential equation of any order. Yes. We start with the f to the n. F to the n, this is Sn minus 1, Sn minus 2. You lower the power of the s, you add it to the order of the f here. We start with f of 0, f prime of 0, to see f prime of 0, f double prime of 0, up to the n minus 1 to the 0. In any order we can write down. See, I have the 1, the first, the second, and the third, and by induction, you can have the n. Any question? We are ready to solve differential equation now. Write it down. I'm telling you that how we're going to do it. Yes. Now, when it's going to be an actual number, then you will see it. But you have to know that you start from the top going down. Okay, and you get only Laplace transform for the first one. The other one just. So this means you have to be given the f of 0, otherwise you can't do it. Initial condition, we need initial condition to be able to do it. Now, so what we can do is we can solve a differential equation, a linear differential equation with a constant coefficient. Linear differential equation with a constant coefficient when the initial conditions are given to you. This is the condition they're going to do, okay? You can apply it with some other, but you need a little bit more to be able to do it. But for the time being, everything we did before. That's why previous method, remember, you're using undeterminate coefficient. This is the way you did it. And at the end, you know, you may be asked to find the C1, C2, C3. But this one automatically will give you everything. It's very nice method. Okay? So let's try it. See how good. Now, how are we going to solve a differential equation? In order to do the differential equation, as I told you, the condition is the coefficients are all constant. Okay, the coefficients are going to be all constant, and they're going to have initial value. Initial value means if it's a, you know that if it's an order 1, you get f of 0 only. If it's a second order, you get f of 0 and f prime of 0. So what we do is we assume that the solution to the equation is y equal to the f of t. That's it. We usually go with the t rather than the x. Then you are going to take the Laplace transform of both sides of the equation. Remember, your equation is linear. So all the coefficients will be out. The leftover are going to be what? Depends. The leftover would be L of y prime, L of y double prime, if it's of the second order. Use this formula. You change everything to the L of t, Laplace of the f of t. You combine them together. On one side of the equation, you get L of f of t. On the other side of the equation, we get another function. We are going to call it g of s, if you like. Then we use the Laplace inverse. Automatically, we can f of t. Okay, so that's why we studied Laplace inverse first, to be able to get through it, okay? It takes time, depends on the situation that we have, but that's a very nice method, really. Very nice, I mean. Okay, so we give you instruction, and then we are going to do it. As I told you, we are going to have 3 types of the equation tonight. Before this quiz, we're just focusing on the first type, but we prepare you for the second one, or the big one. So we give a remark of how we're going to solve a differential equation with Laplace transform. Remark. Okay, there you are. The Laplace transform. The Laplace transform can be applied. Okay, can be applied to solve. Look at the condition that we should have to solve a linear differential equation. Linear differential equations with constant coefficient, with constant. This is the only one that we can use with the constant coefficients. Okay. With the given initial condition. initial conditions. Initial condition is going to be at 0. Now, what we are going to do in this method, okay, in this method, assume that y equal to the f of t. I change it. Some people, they don't change it. They start with the y prime, y double prime. It's not a good intention. So in this method, assume that y equal to the f of t is the solution. Is a particular solution, okay? Is the solution of the given equation. Given equation. Okay, that's it. Now, what you are going to do is, this is the first step. The second step is take the Laplace transform. The Laplace transform of both sides of the equation. Of both sides of the equation. Both sides of the equation. It may be homogeneous or maybe not, okay? We work with the homogeneous for the time being, but we give it. Okay, take the Laplace transform of both sides of the equation and use, okay, the previous theorem that we talked about. Use the Laplace transform of derivatives. Okay, this is the one that I talk about it. I rewrite it again. I mean the Laplace of Fn of t is equal to the s to the n Laplace of f of t minus s to the n minus 1 f of 0 minus s to the n minus 2 f prime of 0, just going up to the minus f to the n minus 1 at 0. Okay, you take the Laplace transform on both sides. You use this theorem to change the equation into the, okay, derivative and simplify. Simplify the equation. Okay, to convert it into the form. Into the form. This is what you get. You get the Laplace of f of t to the left and on the right. On the right is going to be a function. It's going to be a function. I'll call it g of s. So on the first part, to the left, you get Laplace of f of t. To the right, if there is going to be something involved, you already got the Laplace transform of those. Then the solution is going to be, then you take the Laplace inverse. F of t equal to the Laplace inverse of g of s is the solution of the equation. Is the solution of the equation. And you're done. This is the way we do it. Yes.
And then would you want us to like isolate any of the specific variables on the differential solution?
Everything would be nice. You don't have to do anything about it. You get a nice solution. There is nothing to be done. Okay, it's a very nice method. So let's take a couple of them. So I'm going to do it. That the last part of the Laplace inverse, you got to be careful. We talk about it tonight. The way we are doing, you have to modify it, okay? that job is going to be, your job is going to be that last part. If it's going to be kind of application problems with the piecewise different function, but it's fine. We can do it. Okay, are you ready? Let's do it. Example. We want to solve differential equation by Laplace transform. Solve each equation, differential equation, differential equation using Laplace transform. Laplace transform. Remember, this is the only method that you're going to apply. Don't say, I know another method to do it. You have to do the Laplace transform. There's no way that you are going to escape from this one. Okay. The first one. The first one is this one. You have a y double prime minus y prime minus 2y equal to 0. Initial conditions are y of 0 is equal to 1. Y prime of 0 is equal to this. That's it. But I prefer the notation f of t. If you are happy using the notation of y of 0, y of t, we don't mind. But that would be more familiar. Okay, that's it. So what we are going to do, solution. I'm going to suppose, okay, suppose y equal to the f of t is the solution. Solution with initial condition that I have, I change it to the f. F of 0 is equal to 1 and f prime of 0 equal to this. That's what I have. So I take the Laplace transform on both sides with this new notation. So it's going to be the Laplace transform of, and this is going to be f double prime of t minus f prime of t minus 2f of t. And on the other side, I have a Laplace of 0. You may have something else. This is homogeneous. But that would be too much for the first example. Now you know that Laplace transform is linear. So distributed any coefficient, you can put it out. So that give a Laplace of f double prime of t minus Laplace of f prime of t minus 2 times. Okay, 2 times Laplace of f of t. And on the other side, Laplace of 0 is 0. If it's going to be anything else, you find the Laplace transform. It's going to be cosine x on the other side. So the Laplace of cosine t or cosine x would be s over s squared plus 1. Okay, but in this case, it's 0. That's a step 1. Taking the Laplace of both sides. Now, change the derivatives with the formula that we have. Okay. Carefully substitute the first one. Second order. For the second order, we start with the s squared, Laplace of f of t. Lower the s, lower the power, s times f of 0 minus f prime of 0. That's the first one. Laplace of f double. Just the formula. Laplace of second one, we proved it. You see, we start with the s squared, Laplace of t. We lower the s, x, f of 0. This is s to the first. This would be s to the 0. You don't have it. You go with the f of 0, f prime of 0, f double prime of 0. Depends how many times you go forward. Okay? So the next one, minus this one, you see? The power is 1. So it's going to be s Laplace of f of t. Then lower the power of s. This is going to be nothing. S to the 0. So it's going to be minus only, okay, minus f of 0. Remember the order of derivative. This is the second order. You end up with the first. This is the first derivative. You end up with the f of 0, like the general formula. You see, look at this one. You start with the n, you end up with n minus 1. Any question? And the last term as is minus 2 Laplace of f of t equal to the z. Now substitute the initial condition, simplify. So the initial condition that you have, I just remind you have the f of 0 is equal to the 1, f prime of 0 equal to the z. So go back, substitute. You see f of 0 is 1, so this would be 1. F prime of 0 is 0. Then f of 0 is 1. So if you go back and simplify it, so what are we going to have? It's going to be, this is going to be s squared Laplace of f of t. That give you minus s, because f of 0 is 1. This would disappear. Apply the negative sign, so it's going to be minus s Laplace of f of t. Okay, and negative positive, plus 1. Okay, minus 2 Laplace of f of t equal to this. I just substitute the initial conditions. Now you'll be able to factor out, you simplify this Laplace of f of t's. If you cannot simplify it, you combine the like term, then you put it out as a factor. Okay, so this is what you have. S squared s 2 L of t. So put them together, the coefficient would be, you factor out s squared minus s squared minus s minus 2. Laplace of f of t. Move everything else to the other side. So it's going to be equal to, on the other side, you get a positive s, and you get the minus 1. See, that's going to be the conclusion. So that's why I was talking about f of t on one side, then the g of s. If you've done this one so far correctly, you should look at this one. S squared minus s minus 2 must be a characteristic equation of this homogeneous linear equation. Remember, the characteristic of this one is what? Is r squared minus r minus 2. So it's going to be s squared minus s minus 2. If you don't get it, you have to go back and correct it. It's always the case for all these problems that we're going to do. This must be a characteristic equation corresponds to that homogeneous one that you are going to have. Okay, this is one sign that so far, so good. Now find Laplace transform of L of t. So Laplace of f of t. Laplace of f of t would be equal to what? Is equal to the s minus 1 divided by s squared minus s minus 2. That's what we were talking about, you see? We said solve it, solution, simplify it, write it down. It's a Laplace of f of t equal to the function like gs. Now you take the Laplace inverse to get the t, f of t. So f of t, is going to be Laplace inverse of what? S minus 1 over s squared minus s minus 2. So your job is to find the Laplace transform of this one, and you know how to do it. You have to use partial fractions. There are some other methods to do it, but for the time being, s squared minus s minus 2 is factorable. When it's a factorable, you just use partial fractions to find it. Okay, any question? So the rest are going to be just the algebra of this part. Are you done? I have to go to the next page and work on that partial fraction part. So this is it. So what I have to do is, this is s minus 1 over s squared minus s minus 2. So that will be s minus 1 on the top. Okay. And this is going to be s minus 2 times s plus 1. So we write it as s minus 2 plus s plus 1. So something like a1 and a2. And just continue to get the a1 and a2. Okay, so the common denominator would be s minus 2 times s plus 1. Okay, so the top is going to be a1 times s plus 1 plus a2 times s minus 2. We let the top to equal to each other to find the a1 and a2. a1 times s plus 1, okay, plus a2 times s minus 2 is equal to the s minus 1. You know that you need two numbers and the numbers are available. You take the s to be equal to -1, so this would be 0 plus a1, a2. a2 times -1 minus 3 equal to the -1 minus 1. So that gives me -4a2 equal to the -2. So the a2 would be 1/2. So that would be a2. You go back, the other number is s equal to 2. S equal to 2, that gives me a1 times 2 plus 1 plus 0 equal to the 2 minus 1. So that gives me 3a1 equal to 1. So a1 would be 1/3. Yes.
Wait, I'm a little bit confused. The one from A2 is multiplied by s minus 2, but then it's now it's A2 being multiplied by -1 minus 3. I'm confused on where the negative.
What's that?
I think you're
This is a1 times s plus 1 plus a2 times s minus 2
right.
equal to the s minus 1. So I put s equal to -1. So this would be 0, -1 minus 3, -4. I got the a2.
-1 minus negative, minus 2, not minus 3.
Yeah, the three.
Oh, okay. So that's -2. So this is 3. Thank you. So that give you what? 1/3, 2/3. Okay. So the a2 would be 2/3. Okay, that's fine. Thank you. Hmm? You got 3/2? No, you don't accept. Okay. I haven't got the solution, so you are right. Okay, so go back and substitute, get the Laplace inverse. So remember, you're looking for this Laplace inverse. Laplace inverse of s minus 1, s squared minus s minus 2. So now it's going to be Laplace inverse of the first one. What's a1? It's going to be 1/3 over s minus 2 plus the Laplace inverse of a2, 2/3 over s plus 1. You know that you put out those numbers and they are all exponential function. So this is going to be 1/3 e to the 2t plus 2/3 e to the -t. The final answer. Remember, we're just using this fact that the Laplace of e to the at is 1 over s minus. You see, nice. We got the solution. It's going to be solution of the equation without any constant, because this is a particular solution. Because we did have those conditions at 0. You see, it's a straightforward problem, but you know, we've got to be careful in the last part. So I can give you a break. We come back and do one more. And then in order to get to the second group, you have to work quite a lot to get to that one. So we prepare you for the second group. But on this quiz, you are going to have only of type 1 of this type of differential equation. Okay, you got 10 minutes, and you have to introduce the new method. Let's go check.
I was so confused on this part. Like, how did you end up getting ones? And I don't know how.
Even do see f prime of 0 is 1,
Right.
see f of 0 is 1, f prime of 0 is 0. Just substitute.
So you said that's the
Bring it
form.
here because this is.
Okay. Okay. Huh?
Okay, come here.
Oh.
No, I've been posting this one. I've been like. I don't. Oh, within your rankings, always you have to solve them. That will be one of the. Yeah. You start with y to the f of t. You get the Laplace transform, always believe you never do. Now you have to substitute for f of 0 and prime of 0. That's given. F of 1, prime of 0 is 0. So you go back to the f of 0, and you 1, and then you have s. Good. Yeah, I like it so much.
How did you get minus? Oh, X. Okay.
This time, f of 0, f of 0,
Prime of 0.
f prime of 0 is 0.
Minus S minus.
I wouldn't want to do this one.
No.
I feel like I need to.
See the Laplace of the prime, you have to stop it from Laplace of the prime, is the one that will move into that. This is the board.
I'm assuming it, yeah,
Like, wait.
that makes sense, right?
Then you substitute again.
Then we got to.
You substitute for f of 0 is 1.
Oh, I did not take.
Okay, you're going to have lots of these. F of 0, prime of 0, f of 1 of 0. And you simplify it. You see, after that, you substitute 100, you have something to find. You need to have that. You have to have the.
I don't.
L after sign, L after.
Let's see. So, let's see that.
Right goes up to the 4 point. Yes. You like so shocked in your idea, so you have to do it more. See?
So I just wait, so. I must be like just right after W. Oh. Oh, okay, but
That's it.
I got an 87.
Yeah, you can write it down, so I didn't see it.
okay, yeah, also,
That takes time. Write it down correctly.
okay, so I should put.
Yeah, because I don't have time.
Okay.
If I don't see it, I'll draw.
Okay. And then also, this was the, I don't know why you wrong, but this was the same. Oh, just so I just have, I said K equals.
No, you have a great application.
Right. So, so I just split them in half and then factor out the C.
If you're down, I just, I get the call. Still,
Yeah,
so
that makes sense.
basically that.
Because it's not showing you now.
Because. But then I was like, if there's a-
okay,
Because we got here,
right,
I think they put it together.
yeah. Okay. And then also,
I had done the thing, I lost.
no, because I got 22 around here, right?
So you have to drop the lowest one.
Right, so then, yeah, I think you give me. Okay, well, if we count it up, this was, we.
Oh, yeah,
I don't know.
Okay, okay.
Let me add them together.
I don't know. I'm like.
Yeah, yeah.
Oh, I want to use that. I want that.
I see.
Why did you show I put so many more. So I want to make. I go to it right away. I want to be that one. Okay, I don't know.
Yeah.
That's good. Like, there's like, I don't wanna-
Doctor, you need to come.
You're in a way.
Okay. Yeah.
No, I want to do it. Yeah. I want to just wait.
No,
Yeah, I like the. Yeah.
No, I have my coworker right now, or like, yeah, these are best, engineer, factory director, driver, they're. Everything is not. And it's like, I work 9 to 5, right? Then from 5 to 8, all the way up to the like, that's why I do, and then on my, I don't know, Friday to Saturday. Yeah. No. I don't know. Yeah. Yeah. Like, I know it is, I'm saying, like, there has to be a certain. I don't have time to deal with it right now. I don't want to do it. I want to do it. Oh, yeah. 5 years into my career. Like my dream is below.
Yeah. Yeah, we got to post like.
Okay, let's have another one with a higher order.
No, I.
Okay, number two. You want to solve this equation? Y to the fourth minus y equal to the 0. And these are going to be the initial condition. Y of 0 equal to 1. Y prime of 0 is equal to the 0. Y double prime equal to 1. And the y tiers of 0 equal to the 0. You know, this differential equation of the first order. So we should have 4 initial conditions. And you have it. Y of 0, 1. Y prime of 0, 0. Y double prime of 0 is 1. And the y tiers, if you like, the third order, is equal to the 0. So we want to solve this equation using the Laplace transform. Okay, there you are, solution. You assume that this is the way I do it. Assume that unless you like to go with the y. So suppose y equal to the f of t is the solution. Okay, solution with these conditions. So the condition would be f of 0 equal to 1. F prime of 0 is equal to the 0. F double prime of 0 is equal to 1. And the f third, if you like, or the third derivative at 0 is equal to this. Okay, now take the Laplace transform of your equation. So now your equation will be changing to the Laplace R. F, the fourth derivative of f of t minus f of t equal to the Laplace of 0. Okay. Now we distribute this one. Laplace transform is linear. So it's going to be Laplace of f to the fourth at t minus Laplace of f of t. Okay, Laplace of f of t is equal to the 0, which is the Laplace of 0. Now substitute. You have to substitute for the Laplace of the fourth derivative or fourth order. Okay, so remember the formula, start with, this is the fourth order. So we start with the S4 Laplace of f of t. F4 of Laplace of f of t, you lower the power of the s. So it's going to be s cubed times f of 0. You continue. S squared times f prime of 0. Okay, minus s times f double prime of 0. And s to the 0 power, but this is going to be f to the third. Okay, third derivative of 0. Remember, when it's a fourth, you end up with the third order of the derivative. Okay, s4, s cubed, s squared, s to the 0. The first one is going to be Laplace of f of t, then you get f of 0, f prime of 0, f double prime of 0, f tiers. Okay, minus Laplace of f of t equal to the 0. Any question? So that theorem that we talk about it, you should be able to do it with any order. Now substitute the initial condition. So initial condition that we have, I repeat it here. So I have f of 0 equal to 1, f prime of 0 equal to the 0, f double prime of 0 equal to 1, and the third derivative at 0 equal to this. Substitute. So when I substitute, you see f prime of 0 is 0, so this would be 0. F tiers is 0, so this would be 0. So for the rest, f of 0 is 1, so that give me 1. F double prime of 0 is 1, so that give me 1. So what's going to be the leftover? The leftover would be s to the 4th power Laplace of f of t minus s cubed, because this is 1. This is out, minus s, because this is 1, minus Laplace of f of t equal to this. So you put the L of f of t together and we move everything else to the other side. So what we have is this one. You have S4 Laplace of f of t minus the Laplace of f of t. Everything else to the other side. S cubed minus s. So you factor out L of f of t. So the leftover is going to be s to the 4th minus 1. Okay. Plus, yes, thank you. As you can see, s to the 4 minus 1 is characteristic equation of this homogeneous, linear homogeneous equation, okay? So this means we are fine. So it's equal to the s cubed plus s. So for L of f of t, Laplace of f of t, so that give you s cubed plus s over s to the 4th minus 1. Okay, if you factor out the s, you'll be able to simplify this one. That give you s squared plus 1 and the bottom one. So this is going to be s times s squared plus 1. And this would be s squared minus 1 times s squared plus 1. So these two will cancel out. So you arrive at, so the Laplace of f of t is going to be equal to the s over s squared minus 1. And f of t would be Laplace inverse of s over s squared minus 1. S over s squared plus 1 is cosine of the t. If you are familiar with the hyperbolic function, so s over s squared minus 1 will be cosine hyper of t. Are you familiar with this from calculus 1? No? Okay, you have to pay for it. So s squared minus 1, factor it. Okay? So this is, you can use that because that would be useful. I'm going to write down for you. But you know, it's okay. You have to simplify it. Okay, any question? Let me just remind you. So if you want to know them, you see that's for your information. It's like the sine and the cosine that we use. And this is it. We define the sine hyper of t is going to be equal to the e to the t minus e to the negative t over 2. Cosine hyper of t is e to the t plus e to the negative t over 2. In the case of the trigonometric function, sine squared plus cosine squared is 1. In this case, cosine squared minus sine squared is equal to 1. So we have similar property. You know, the sine and the cosine comes from the circular functions, okay? Because the unit circle, this type of information coming from the hyperbola, x squared minus y squared equal to the 1. It's the same thing over here. If you use this type of notation, so this formula would help you quite a lot, and we accept that. You see the Laplace of sine hyper of t, sorry, let's give you something like at, okay? So Laplace of sine of hyper of at. Remember the sine of the t was a over s squared plus a. This is going to be a over s squared minus a squared. And the Laplace of cosine hyper of AT. That give you A over, sorry, that give you S over S squared minus A squared. So it would be very useful. If you don't know it, you can, you can factor it. Yes, sorry. Both of them would have S squared minus A squared. What do you mean? The first one is A over S squared minus A squared. The second one is S over S squared minus A squared. In the case of the sine and the cosine, it's plus. In the case of the sine and cosine, it's plus. In this case, it's a difference. That would be very helpful. Okay, but otherwise, you know that you can. I do both method for you. So in this case, the function was. So in this case, f of t was the Laplace inverse of s squared minus 1. So s squared plus 1 would be cosine t, but this one would be cosine hyper. So this is going to be the solution of your equation. And in your language, this is going to be 1/2 of e to the t plus 1/2 of e to the negative t. Okay, if you miss it, method 2, but you better memorize this one will be useful for you. Okay, because the matter is the time that you have to spend to get the solution of these equations. If you don't like it, it's very easy to factor out. You see that give you s over s minus 1 times s plus 1. So that give you s minus 1, okay, plus s plus 1. And you can call it A1 and A2 to find it. But this is going to be the case. It's going to be 1/2 and the 1/2. With the 1/2 s plus 1 plus 1/2. And if you put the negative sign here, this is it. You call it A1 and A2 if you like, you can find it. So as you can see now, the Laplace inverse of s over s squared minus 1 would be the Laplace inverse of 1/2 s minus 1 minus Laplace inverse of 1/2 s plus 1. So the first one would be 1/2 of e to the t, and the second one would be 1/2 of e to the negative t. I didn't miss any. It's a 1/2 s. I'm sorry, this must be positive because I need the s here. So you can try it if you don't believe it. So it's going to be the same thing, but knowing it, the other one is useful. Okay, yes.
You want to accept cosine I t?
What's that?
You want to accept cosine I t?
No, 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 no complex numbers here. No. No, you're not that. You can define the cosine and the sine. Your difficulty then it's going to be because our idea are all real functions. Then when you go to the improper integral, then you'll be in trouble. And that's why, no, except this one.
Wait, so this breaks if you're in the imaginary plane?
Then you need to do the modification. It's not the same thing.
So you would transform it from the imaginary plane to the real plane? Or how would that work?
We do have the corresponding properties.
Oh, okay.
But over here, in this case, the function is a real value function.
Yeah,
So the situation for derivative and everything will be different.
okay.
Okay, so you can use this one, okay, if you need it. Yes,
Would we need to put it in this format or if we leave it as just
what do you mean?
This is that the answer that we got to.
It doesn't matter. If you do this method, you don't, this means that you are not aware of the cosine of the hyper of the, no, it's the same. But we prefer the first one really, get it. You see, it's not going to be, sometimes it's going to be more complicated. You are going to simplify all these formulas. At the end, you will see, it's not the case that always you have to do all these, operations to get through it. And so it's nice to show it, okay, or to know it. So that's it. You have two of these y to the fourth in your book. I changed the initial condition, so I get this cosine of hyper t. If you check your practice quiz, you have another one. And that may be different. You are going to check it on Wednesday. Okay, so this is the type of, we can make it a little bit more involved. We can replace that 0 with something else, but we are going to do it slowly, if you like. So that's a type 1. This is 7.2. Now we got the good idea of what is, okay, Laplace transform is capable of, if you like. We get this property to be able to do it. Now, the difficulty is, as I told you, when you are getting to the application problems, your functions are not going to be just straightforward. Most of the functions are going to be, okay, piecewise defined function. When you are going to be in application problems, especially if you do something in electrical engineering, etc., there is one function that we use for all the properties. And if we're going to math measure, this function can be used for all type of advanced integrations. This function is going to be called a step function or unit step function. You may have seen it a little bit in college algebra, but they don't usually teach it, okay? Or in calculus. You may have seen it in calculus. If you have something, we call it bracket function in calculus. Again, we don't care. We are going to give you what is this type of function is, and what is going to be the relation with the Laplace transform. Quite a lot, okay? So let's practice this function first, and that will enable us to be able to solve the second type of the differential equations, okay? So let's go back to this function, okay? Before getting to the, okay, this must be a part of next section. You can call it 7.3, okay? This is it. It would be very dense section. Let's see if we can try this one. So we are starting by looking into this a step function, okay? You have to get to know this function quite a while, quite a lot, then be able to do the differential equation. So what's going to be a step functions? A step functions. Okay, this is going to be, I just want to give you a short version that I have for the the step function. This is the definition of the step function. We start with the number c. This is a standard. Suppose c, the constant, is a number, is a non-negative number. It's going to be a fixed number. Okay, now the step function or the unit step function. The unit step function. Unit step function is denoted, okay, denoted by this notation, UCT. We use the variable t because it's coming from application problems. C is the base, if you like, UCT, and is defined by, and is defined by, this is the definition. UCT is going to be equal to, is equal to the 0 if t is less than c, but is equal to 1 if t is greater than or equal to the c. So we break it at c, if you like. That's one. It's a piecewise defined function. We break it at c. So if you want to graph it, This is going to be the graph. Okay, C is a number. If t is less than c, the function is 0. 0 is just the, okay, the x-axis. So suppose the c is here. If the c is going to be here, when t is less than c, you get just this part of the x-axis. It's not defined at c, you make a hole here. Then for t greater than equal to the c, this is equal to 1. So 1 unit, if this is going to be 1, so your function starts from here. This is unit step function. 1 step, that's it, unit. It got different names when you know a different notation when you go on in the application problems. It is a piecewise different function. It's piecewise different function, you know, it's discontinuous at C. Because the right limit and the left limits are different that you're going to have. Okay, but it's continuous to the right of the C. Continuous to the right because you have this line here. But at C equal to 1, this is 0, 1. But sometimes we need the complement of this. So the format is going to be in application problems. Note that sometimes we need this function, 1 minus UCT in the application. Sometimes they like 1, 0 rather than 0, 1. If you consider 1 minus UCT, when t is less than c, UC is 0. So that gives you 1. If t is going to be less than c, okay, and the second part, 1 minus 1 would be 0. So that would be 0 when t is greater than equal to c. Okay, so that would be unit step function. Eventually, we are going to find the Laplace transform of this function and something else that will be associated with this one. So that's why we would like you to be able, if other piecewise defined function would be given, would like you to be able to write it down in terms of the unit step function. So I'm going to give you some examples to see how we're going to write it down. Okay, example. You know that otherwise you have to go with the formula to get these numbers. You have a collection of these type of problems. Would like you to write, yes?
For the second one, 1 minus UC of 2, why is it 1 and not negative 1?
Just substitute. If t is less than c, UC is 0. So 1 minus 0 is 1.
Oh, okay.
The second one, 1 minus 1 is 0.
Okay.
Okay. So let's see how we're going to write some function with this notation. So I would like you to write, okay, each function, write each function in terms, okay, in terms of a step function, unit step function. Okay, function, using this notation that we talked about. Because this is the way we are going to do it when you get the Laplace transform. Okay, are you ready? The first one. The function is f of t equal to the 0. Is equal to the 0 if t is between is less than 3 pi half. Just give you a kind of application problem. Is sine t if t is greater than or equal to the 3 pi half. Okay, just compare it with the definition that you have. So the partition point, you see, the partition point is 3 pi half. So c is 3 pi half. If you want to change it, you need 0, 1. You need a 0, 1 in this case, okay? So you have to make this one into 1. What you can do is, you can factor out the sine t out, because the first part is equal to the 0. You get this one? So the solution is going to be, you can rewrite it as, you see your f of t is going to be equal to the like sine t times this function. Okay, so it's going to be less than. Okay, let's see. Okay. Bing.
So the old CRT TVs.
Hmm? No, I don't know what's wrong with this. Because maybe the system. Okay, got that. Okay, let's go on. Pull out the sine t as a factor. So what's going to be the leftover? This is going to be 0, 1. Because the sine t times 0 would be 0. Sine t times 1 would be just sine t. And this is going to be true when t is between 0 and 3 pi half, and t greater than or equal to the 3 pi half. But the leftover is the unit step function. So you get f of t is equal to the sine t. Okay, the first one's going to be sine t, and the second one would be unit step function. The base is 3 pi half of the t. Usually this is the way you write it down. It's going to be unit step function at the base 3 pi half of t times the sine of t. Later on, you will see that it's important to be able to write it down because you need to find the Laplace transform of this type of function. Of course, you can use the definition to find the Laplace transform. You break the integral and you get this result. Okay, so this is the first one. Any question? So it depends on the problem, yes?
I'm sorry. Why didn't you call the thing out?
You see, the unit of the step function is 0, 1. So you already got the 0. You need a 1 here. It's like dividing by sine t.
Okay.
Then you check it, of course. You see, you checked it. Sine t times 0 would be 0. Sine t times 1 would be sine t. Okay, you may have to do some algebraic operation to get to that one. Okay, now let's see if you like the next one. Okay, the next one. The next one is this one. F of t equal to is equal to the cosine of t. Cosine of t if t is less than 2. But is equal to the cosine of t plus sine t if t is greater than or equal to 2. You see this function? You want to write down as a unit step function again. So you partition it at 2. Any suggestion for this one? Of course. You have extra term. You see it's cosine t plus sine t. So what you have to do is you have to break it. You break it into 2 functions. The first function is cosine t because you have cosine t on the top and the bottom. You see, this is going to be the solution. You're going to rewrite it. F of t equal to the cosine t, now plus. Plus what? You take it from the top, so the leftover is going to be 0. You take it from the bottom. The bottom one would be sine of t. So t is less than 2, and t is greater than equal to 2. You see? Now you bring this, you pull out the sine t, as we did it for the other one. So it's going to be cosine t plus sine t times it by 0, t less than 2, and 1, t greater than equal to 2. Now we get to the unit step function at the end at the base 2. So what's going to be f of t? F of t would be cosine t plus, that's just u2t. It's going to be ut of t times sine of t. Okay, so that gives you an idea of what we are going to do with this type of function that we're going to have. We are going to use them. Okay, later on, it's going to be useful. Okay. Yes, what's the question? No. The 0, 1 is just the formula that we have. 0, 1 is u2t. It's not 1 minus. 0, 1, okay. The sign is like the previous one that we did. You see, the previous one is 0 sine t. It's the same function, but the base is different. Because it's a sine times. You see, if you pull out the cosine, it's cosine t plus, and then that. Okay? Be quick.
How do you know that? It's unit 0, 1, not 1, 0.
It's a formula. What's the u function? U function is 0, 1. And you want to change it, you need the step function. Okay? Now, let's see. How are we going to find the Laplace transform of this type of function? Okay? So Laplace transform of this is it. We can write it as a theorem or we can find it.
Is this still 7.3?
Yes, 7.3 up to the Wednesday. It's very dense section. Okay, so how are we going to find the Laplace transform? That's the important part. Laplace transform of the unit step function, UCT, of the unit step function. You know that this is going to be what? UCT. Okay, just use the definition to find it. Remember, that's it. Note that. Let's start with the definition. What do you have? UCT is equal to 0 if t is less than c, 1 if t is greater than or equal to the c. Find the Laplace transform using the definition only. So what's going to be the Laplace transform? Laplace of UCT. Remember the formula? 0 to infinity, e to the negative st, UCT, dt. Your function is a piecewise defined function, so you have to break the integral. You break it for t less than c, t greater than c. So we rewrite it as 0 to c, okay, e to the st uct dt plus c to infinity, e to the negative st uct dt. Now substitute. When t is less than c, the function is 0. So that would be 0. So the first one would disappear. When the t is bigger than c, the function is 1. So we arrive at integral of c to positive infinity e to the negative st dt. Now integrate it. How we're going to integrate it is the limit of, let's say t goes to b, integral of c to b, e to the negative st dt. So the integral of e to the negative st dt is what? Is the limit of t goes to b. Exponential function never change, e to the negative st, but you have to divide by u prime. What's your prime? Negative s. Okay, because you differentiate with respect to the t. Going from c to b, substitute for t of course. So it's going to be equal to the limit of t goes to b. If you substitute b for t, e to the negative sb negative s minus e to the negative sc over negative s, b goes to positive infinity. You bring e to the sb down the denominator, then the limit would be 0. So it's equal to limit of t goes to b. Okay, this would be what? 1 over negative s e to the negative positive sb. And this would be negative positive plus e to the sc or cs divided by s. When the t goes to, sorry, t goes to the t infinity. Yes. Is our own. I'm sorry, I just missed a notation here. Is not t, is going to be b. B goes to infinity because you replace the, okay, you replace the infinity by b. Okay, that's it. This would be 0 now because e to the sb is infinity and on the top is a pizza. So that gives you 0. The result, e to the negative cs over s. Very famous formula. So what's the Laplace of the UCT? Laplace of the UCT is e to the negative cs over s. This is going to be Laplace transform of the unit step function. And equivalently, in order to do it, the Laplace inverse. Okay, and that's it. This is going to be equivalently, you have what? Laplace inverse of e to the negative cs over s is simply what? UCT. So you have to memorize this formula for that second group of the equation that we are going to solve. Yes.
In the case of, sine t, would you incorporate that sign?
You have to wait. You won't be able to do it yet. For the time being, we're just using the unit. Then there is another theorem that you have to do. Okay. Up, down, down, down. Okay, so this is going to be, we need this one when we get to the second group of those, okay, of those equations that we're going to have. Write it down, give you a couple of examples. To see how we're going to operate with these type of problems. Then to see how much time we have. Okay. Okay, so let's find out how we're going to apply it by using it for some problems. Any questions? So add this one to your collection. Laplace of the UCT. Now, the application type so far. Example. Find the Laplace transform of each function. find the Laplace. Okay, Laplace transform of each function. Okay, so the function is going to be the following. Number one is, I'll just give you one for this case. Okay, the function is f of t is equal to the u1 of t, okay, plus 2 u3 of t minus 6 u4 of t. That's it. Let's get to use these combinations. Yes,
Will there ever be a function where it's just u at t and we assume the base is one? Or do you
no, they have to give you the base. No, you don't write it in what's called. If it's one, they have to give you u1 of t. Always, same as begin. Okay, so you know that this is a straightforward solution. We want to find the Laplace transform of this function, Laplace of f of t. You know that everything is linear, so it's going to be equal to the Laplace of u1 of t plus 2 u3 of t minus 6 u4 of t. Distributed. It's going to be Laplace of u1 of t minus 2 Laplace of u3 of t minus 6 Laplace of u4 of t. Now apply your formula to each one of them. Remember, Laplace of uct is what? E to the cs divided by s. Yes, what's question?
Where did you get that subtraction from?
That's one. Just substitute. The first one. C is 1. So it's going to be e to the negative s over s. That's the first one. The second one. 2 times. Okay, times c is 3. E to the negative 3s over s. The next one. Minus 6 times. C is 4. E to the negative 4s over s. That's it. We put them together. So the Laplace of f of t is e to the negative s over s plus 2e to the negative 3s over s minus 6 e to the negative 4s over s, and then you done. There's going to be, of course, a combination with other functions, but you have to wait to get to, okay, to get to that part. So this is a kind of getting it in this form. I give another one, the inverse. Ready? Example. So find the Laplace, find the inverse. The inverse of the Laplace transform. Laplace transform. It's very similar to what I did. You begin f of s equal to the following. E to the negative s plus e to the negative 2s minus e to the negative 3s minus e to the negative 4s divided by s is exactly the other way around. So as soon as you see these terms, e to the cs, you know that this must be done by the unit step function. Okay, so we'd like to find the Laplace inverse. What is Laplace inverse of fs? Now you break them. You write it down as Laplace inverse of e to the negative s over s plus e to the negative 2s over s minus e to the negative 3s over s minus e to the negative 4s over s. Okay, so that would be Laplace inverse of e to the negative s over s plus Laplace inverse of e to the negative 2s over s minus the Laplace inverse of e to the negative 3s over s minus the Laplace inverse of e to the negative 4s over s. You compare it with the formula that e to the cs over s is the Laplace transform of uct. So the first one, what's the first one? U of what? U of 1t. Second one, 2t, 3t, and the 4t. And you're done. It's the way we're going to use it, okay, for the direct one or indirect one. We get these numbers done. Okay, any question? Now, there is one theorem that I'm going to write that theorem so that we prepare to be able to practice for Wednesday. Now, when you do this UCT with the combination of functions, you see, suppose you have sine of t UCT. So I'm going to find the Laplace transform of that one. So there is one easy way to do it for this type of function. So I'm going to write the theorem and then I explain it for you. The way we're going to do it, we call it there are a kind of two famous theorem in these sections. We call it a kind of translation. We call it the translation theorem, if you like in algebra. In algebra, you graph a function y equal to the x squared. If you know the y equal to the x squared, then if you give y equal to the x minus 1 squared. So we can use that part in order to do it. So it's a kind of similar one to this one. The similar one is going to be in this form. If let me write down the theorem because I don't have time, but I want to make sure get this at least I write it down. There are two, but before this quiz, we are not going to rush it. We give only one of them, the first one, and we leave the second one before the test. Okay. So what is the actual? Want to make sure you get it right here. Okay, find it. I don't know what the theorem is, but I want to make sure you get the condition all right. Okay, this is it. This is the first translation theorem. Theorem is a great theorem. You need this one for solving all those type 2 differential equations. What is this? You see, if we know the Laplace transform of one function, if you know that the Laplace of f of t is already given to you, and you call it f of s. If this is given, exists, it's some initial condition that we need for s to be bigger than a number, we call it a, and that will be positive. These are the conditions that we need to be able to talk about the Laplace transform. And c is going to be a positive number. A positive number. If this is going to be the case, then look at this one. Then the Laplace transform of UCT f of t minus c. UCT f of t minus c is simply equal to the e to the negative cs Laplace of f of t. And the Laplace of f of t is already given to you, which is equal to the e to the cs f of, okay, f of s. So that's it. That's a great formula that we're going to use. Laplace of uct f of t minus c is simply e to the negative cs fs. We call it the translation. This means if you go to your function, which is f of t, you replace the t by t minus c, you have to pay for it. So what you pay? You multiply your Laplace transform by e to the negative cs. That's why they call it a translation theorem. And equivalently, okay, and this is what we need for the Laplace inverse. Laplace inverse of e to the negative cs fs is simply uct f of t minus c. This is the one they call it, the translation theorem. It's very easy to operate and easy to prove. You write just, I prove it next time for you. It's going to be just a definition of integral. Just use a kind of substitution method for the t minus c. Yes.
So we're solving.
So would like to answer in your question. For example, if you have something like what? UCT sine of t. So what is your c?
One.
If c would be 1, if c would be 1, in order to be able to do it, you should have what? UCT sine of the t minus 1.
Okay.
So for this type of function, they are not going to give you 1. They give you something like u2, u2 pi t, u pi t sine of the t. Then what you do is you change the t into the t minus pi. The sign would be the same. Then you can apply this one. So you have to modify yourself. I'm going to talk about it. It takes time. Okay, this is where we give you the quiz.
And then.
Okay.
For the inverse one, if we.
For the inverse one, it's much, much easier.
Yeah.
So you see that e to the cs, then what you do it, you keep it. Because you know that e to the cs will create uct. Then you go and find the Laplace inverse of f of s.
Okay.
But then you find it, you find f of t. But you have to change it to the t minus c. Yeah. Okay. Okay, so we need to practice on this one. This is where we give you the quiz, okay? That's fine.
There's a difference between we can say one certification without.